All right, now let's introduce, it's my great pleasure to introduce Professor Henri Darmon from McGill University. He's going to talk about explicit class field theory, a status report.
To Ling. I'm very happy to be here. I have very fond memories of this conference 10 years ago when it was marking the birthday of Winnie Lee. And so I'm very happy again to be participating in it 10 years later. The title of my talk is Explicit Class Field Theory, and I wanted to give a little bit of an overview of some ideas. Oh, I can, okay. Thanks. That have been introduced into the subject over the years, and particularly, I think it's a subject that's been moving along very nicely, especially in very recent times. I'm going to dedicate my conference to my lecture to Nicolas Bergeron, who passed away about 2 weeks ago. And I'm going to evoke some of his ideas towards explicit class field theory towards the end of my talk. And in fact, some of these ideas played a key role in some of the recent work that I've been doing with Pierre Charolois, which I'll mention at the very end of this lecture. Okay, so I'm going to start with something very classical, the Kronecker-Weber theorem, which is one of the most, a very beautiful result from the 19th century. And it asserts that all abelian extensions of the rationals can be generated, are contained in fields which are generated by nth roots of unity. And one way of stating that is that all these extensions can be obtained by adjoining to the rationals values of the exponential function, e to the 2 pi iz, at rational arguments. And so there's this nice transcendental function which gives you all abelian extensions. And that leads, of course, to a very concrete formulation of the main results of class field theory for the ground field of Q. And indeed, it plays an important role in the development of the subject of class field theory for other number fields. And there's another situation where we have an equally nice characterization or construction of abelian extensions, which is the case where the ground field is quadratic imaginary. And in that case, we know that essentially all abelian extensions of this K are contained in a field generated by singular moduli. Singular moduli are just values of the modular function J at arguments which belong to K. So this function J, the J function, plays exactly the same role for quadratic imaginary fields as does the exponential in extending the Kronecker-Weber theorem to these ground fields. And the natural question that arises from these two beautiful examples is whether one can have a similar theory that applies to other ground fields, other base fields. And Hilbert was one of the people who kind of put forward this question. He formulated as the 12th of this famous list of problems in his 1900 address at the ICM. And so you could paraphrase this question as asking what functions play the role for a general ground field as trigonometric functions, like exponentials for Q, or modular functions for quadratic imaginary fields. And I think Hilbert's idea when he formulated the question was to approach the problem through the study of the modular functions of several complex variables, most notably the Hilbert modular forms, which are named after him, and study in particular their values at certain special points corresponding to moduli of abelian varieties of complex multiplication, which generalize the elliptic curves with complex multiplication, which play a key role in the theory in the classical theory. More generally, you might want to try to generate class fields of number fields from the values of modular functions on the higher dimensional Shimura varieties, which could be Hilbert modular varieties. And I think that was the setting that Hilbert had the most in mind at the time. But there are other ones, and often these Shimura varieties are endowed with a nice collection of special points at which one could try to evaluate various modular functions, thereby obtaining interesting class invariants. And this general program, which was initiated, I guess, by Hilbert, building on the work of the 19th century, was, I think, brought to its natural completion by Shimura and Taniyama in the 1960s in their book on complex multiplication of abelian varieties. And this work, this extension, covers a broad class of number fields, namely the so-called CM fields. quadratic extensions of totally real fields, which are themselves totally complex, where all the real embeddings have to extend to complex embeddings. And well, of course, what's nice about this work is that it's unconditional. It's in some sense a complete theory. And it's quite, I think, quite a bit in the spirit of the original theory of complex multiplication of Kronecker, Weber, and so on, that developed in the 19th century. But what are the drawbacks? So this theory does not actually completely answer Hilbert's original question, at least if you interpret it in a reasonably expansive way. This point was made by André Weil in a very nice article, which I highly recommend for those who haven't read it, called L'avenir des mathématiques, which was written in around 1950, so a little bit before the book of Shimura Taniyama. So Weil writes, within the framework of abelian extensions, we have also made no progress towards the generalization of Kronecker's dreams of youth, the generation of class fields whose existence is known to us, thanks to class field theory, by values of analytic functions. Although we were able, without great difficulty, to complete the unfinished work of Kronecker and update solutions to the problem of the theory of complex multiplication for imaginary quadratic fields, the key to the general problem, which Hilbert regarded as one of the most important of modern mathematics, still eludes us. One cannot fail to obtain interesting results by examining these questions more closely. So that's what Weil writes in this a very, very beautiful and somehow prescient article in 1950. And of course, the main question after the work of Shimura Taniyama is what can we say about CM fields, about non-CM fields, fields that do not have this particular behavior at infinity, this particular signature. And the first example, of course, are real quadratic fields that escape the scope of this theory. Okay, here's the French translation of that nice quotation of Weil, which I included here for those who are going to maybe get the handout version later. Okay, you don't have to. I come from Quebec, so we always have to put in the French content when we can. So maybe the first progress beyond Shimura Taniyama on this question came with the work of Stark, which still provides an important framework for us with which we approach this question. So Stark was motivated, so he formulated a conjecture which was the goal was to go beyond the setting of CM fields, beyond the work of Shimura Taniyama, and it was motivated by this very classical result, the so-called Kronecker limit formula, which says, I don't know why I say chi is a character. There's no character here. So this is a bit of a typo. I mean, so if k is a quadratic imaginary field, then we can look at the Hecke-L function, or the partial Hecke-L series of the quadratic field, or attached to an ideal class A of that imaginary quadratic field. And the Kronecker limit formula expresses the first derivative at s equals 0 in terms of the logarithm of a quantity, which involves the absolute value of the Dedekind data the value of the Dedekind data function at a point in the upper half plane, which is associated to this ideal class. So here eta is the Dedekind data function, which is a modular function, and so it's kind of in the same category of objects as a J function, modular form, I should say. And so Stark's conjecture was what Stark thought was, well, after all, the left-hand side of this equation, the values of L functions and their leading terms at s equals 0, make sense in a much wider range of settings. I mean, I could consider these values for any ground field. And so what he ventured is that the leading terms of these abelian L series, when they have simple zeros at s equals 0, should recover logarithms of absolute values of units in abelian extensions of the associated ground field. So one could try to construct, thanks to this, abelian extensions by looking at leading terms of L series. Now, the conjecture is still basically open. I think there's been remarkably little progress on this conjecture. I mean, really unconditional progress over the last decades. It's not for want of being studied and so on. Now, so I'll make a few critiques about Stark's conjecture now. So of course, it remains largely open, so it's not clear what kind of tools we could bring to bear on the question. It seems a little bit inaccessible, barring a new idea. And one of the issues is that Stark makes no proposal for what might arise in the right-hand side of this generalization of the Kronecker limit formula, which he predicts. So one can't really try to prove an equality. There's no independent definition of the units which are predicted by Stark's conjecture. And the second critique is that the settings where these abelian L series admit simple zeros at s equals 0 are somewhat restricted by signatures. So like with the theory of complex multiplication, where we can only handle essentially CM base fields, here we can consider, so now if I look at L series of a ground field K twisted by some Hecke character psi, the restrictions on K and psi for the conjecture to be non-vacuous, so to speak, are that either K should be totally real and psi be an odd character at all but one of the Archimedean places of K, or that K should be ATR, which means, so this is an acronym for almost totally real, namely it should have a single complex place, and the character should be odd at all the real Archimedean places. So only in those two situations do we have simple zeros at s equals 0. And in the other settings, we would get higher order zeros, and the unit ranks would be larger, and we would expect to recover regulators, which are determinants of the logarithms of units. But it's not easy from there to extract the actual units themselves. So that's the issue. So then, of course, it's still an interesting conjecture in higher rank, but it does not have, it's not immediately germane to explicit class field theory. And so, yeah, I wrote here something which is maybe a bit too strong than I'm thinking, more strong than I think. I said it says little about explicit class field theory for base fields that have more than one complex place. And in particular, one thing which is notable is that it leaves out entirely the case of CM fields, except for quadratic imaginary fields. So the only ground fields of intersection for these two approaches are the quadratic imaginary fields, which certainly provide a template for a lot of work on explicit class field. Okay, so but one should really think of the approach that was proposed by Stark as being almost complementary, a bit orthogonal to the approach that Hilbert had in mind and that was developed by Shimura and Taniyama. Okay, so yeah, so that's what I'm saying here. So we do not know, for example, what might be an analog of the Kronecker limit formula for CM fields. Is there some formula relating the class invariance you get it from CM theory to L functions? It's not so clear really what to get. This was studied in, for example, in Eyal Goren's PhD thesis, where with the Shalit, they tried to get evidence for the Stark conjecture for quartic CM fields using the class invariance arising from values of modular functions on Hilbert modular surfaces. But trying to get the suitable multiplicative combinations to get non-trivial units turned out to be not entirely successful. And in a similar vein, you might ask what plays the role of the eta function for, say, real quadratic fields or more general base fields. So that's an interesting question that emerges. And another thing is that the theory of complex multiplication itself yields a rich collection of invariants defined over class fields, not just units, which are the things that arise in Stark conjectures, but also things like Heegner points, for example, which arise from taking the modular parameterization of an elliptic curve and looking at the images of CM points, or simply singular moduli, which are values of things like J or so, which are not units that have interesting factorizations, which are interesting things in their own rights. So, and these phenomena sort of escape the framework of Stark's conjecture, at least in the current understanding that we have. Okay, so I'm going to now say a few words about Stark's conjecture for real quadratic fields, where, I mean, one can try to, it's be reasonable to try to ask about things like the Kronecker limit formula. So it's a remarkable observation, which still needs to be better understood, which arose in quantum information theory in the study of configurations of equiangular lines in finite dimensional Hilbert spaces. And these are called SIC problems, I guess, symmetric, informationally complete, positive operator value measures. Now, so this is a kind of a problem of almost linear algebra, almost combinatorial. You try to find configurations in a space of dimension D. You try to find D squared lines where the pairwise angles, their absolute values, are equal for all pairs of lines. And it turns out that these configurations can be found, but when one tries to find them, one finds that there emerges in the study certain Stark units, the Stark units in the Abelian extensions of real quadratic fields. And they arise as somehow as matrix coefficients in certain linear representations of the Heisenberg group. So this was a study by people like Gary McConnell, and then Jean Kopp has done wonderful work in this direction. And I think it raises hope maybe for an underlying geometric structure that would give an independent definition of the Stark units, which one could then hope to maybe relate to these L functions, and maybe this is still a dream, but may try to prove something unconditional towards Stark's conjecture. Maybe the formalism suggests that underlying these are some generalized theta functions or things that look like modular functions that would account for the Stark units. And in fact, Jean has constructed a very beautiful kind of object, she calls a Pockhammer cocycle or something, which arises from the transformation theory of certain Pockhammer functions, and formulated in these terms a Kronecker limit formula for real quadratic fields. I don't know why I wrote conjectural here. So the formula says that certain values of something which is a cocycle, I'll say more about that in the coming slides, is related to the leading term of an L function. That's an unconditional result, and then if you believe Stark's conjecture, you conclude that the invariants that Jean has constructed by this theory give you units and Abelian extensions of real quadratic fields. So it looks like it certainly enriches the picture of Stark's conjecture in the setting of real quadratic fields. Now, a work which I think is also related and has appeared recently is this article of Nicolas Bergeron, Pierre Charolois, and Luis Garcia, which considers the case of cubic fields, specifically complex cubic fields with one complex place. And so what they can do is they construct a certain one cocycle, which I'll call J sub BCG. So it's a one cocycle on SL3Z with values in A star, where A star is the multiplicative group of functions that are holomorphic on certain open subsets of P2 of C, P2 of C being endowed with the natural action of SL3. And this object is constructed in a very classical flavor. I mean, it's a kind of approach which would have been appreciated by people like Eisenstein in the 19th century. It's a kind of a triple sum. I mean, very similar to the double sum defining Eisenstein series, which one kind of gets to converge by a sort of very clever summation process. And what they conjecture is that if T is a torus in SL3Q, meaning, so if a rational torus in SL3 corresponds to, it's an algebra A group, commutative, maximal, its rational points correspond to the elements of norm 1 in an étal in an étal algebra over Q. And I'm going to assume that this étal algebra is actually just a field, so a cubic field. Yeah, so, and then the integer points are just the units in that cubic field. And they focus particularly on the case where this torus corresponds to a cubic field with one complex place. And then the group of relative units is actually of rank 1, like for real quadratic fields. And they take an element of P2 of C, so a line, which is an eigenline, which is spanned by an eigenvector for the action of this commutative group, this torus. And then they define the value of their cocycle at this torus. And this is a very natural definition. You have a cocycle on a large group, you can always restrict it to a subgroup. So they take the restriction of this JBCG to the torus T of Z. Now, you have a map on the functions on the symmetric space, P2 of C, which is given by evaluation at that line V. And because the line is fixed by the torus, the evaluation map is T of Z equivariant, and therefore it makes sense to take the evaluation at V of the resulting restriction. And so you get, at the end of the day, an element in the H1, and you look at the cohomology class only, you get something in H1 of OK1 star with values in C star. But this OK1 star is of rank 1, it's just a copy, it's isomorphic to Z, and therefore this is identified with C star once you choose a generator for that abelian group of rank 1. And this invariant in C star, they conjecture it to be a unit in the narrow Hilbert class field of K. And this conjecture that they formulate is also supported, a bit like in Jean's work in the setting of real quadratic fields, by a Kronecker limit formula, which relates the absolute value of this invariant to the derivatives of related partial zeta functions. So again, it's consistent with Stark's conjecture, but it gives an independent formalism for getting at the right-hand side. And very importantly, it gives a genuine refinement of Stark's conjecture, because his JBCG of T is a complex invariant. And Stark's conjecture knows only about the absolute value. So when you look at the leading terms of L functions, you throw away some information. They actually manage to make a prediction about what the argument of that unit would be. So it's a very beautiful, inspiring work. I think it resonates in a way that we don't completely understand yet, which should be better understood with the work of Jean in the setting of real quadratic fields. Okay, so I'm going to talk about an earlier work now, which I had done with Pierre Charolois when he was a postdoc in Montreal, which considered the case where K is a quadratic ATR extension of a totally real field S. So you take a totally real field F of degree D, and you take such a quadratic extension, and then we were able to construct it in a very straightforward way, a cocycle in a D-1 cocycle on SL2 of OF, so on the Hilbert modular group over F, with values in the multiplicative group of analytic functions on a single Poincare upper half plane. And this was obtained by considering periods of the Hilbert modular Eisenstein series over F. We conjectured then, very much in the same spirit as Bergeron, Charolois, and Garcia more recently in their SL3 situation, that if T is a torus corresponding whose rational points are the unit group of an ATR extension, this ATR extension K, that if we take now a fixed point on the symmetric space for this torus action, then the value of the Eisenstein cocycle at the torus, which is defined exactly in the same way by taking the evaluation. But now we land in HD-1 of OK1 star with values in C star. And because this OK1 star now K has a unit group, the group of relative units of K over F is of rank D-1. So you land in this HD-1 of Z to the D-1 C star, which is, again, after choosing an orientation or something, is isomorphic to C star. And we conjecture that this value is indeed a unit in a narrow relative Hilbert class field for K over F. So this was a little bit a framework that was reminiscent of complex multiplication, where you would take K to be a CM extension, and then you would just evaluate a modular function at some CM point. Here, we're evaluating instead a D-1 cocycle. And again, in this case, we had a Kronecker limit formula, which was already somehow implicit in Pierre Charolois' PhD thesis, which relates the absolute values of these invariants to derivatives of partial zeta functions. Okay, so about one feature of this construction, which is notable and which we don't yet know how to do in GL3 case, that's why I want to bring it up, is that in this construction, we could replace the Hilbert modular Eisenstein series over F by any weight 2 cusp form. For example, one associated to an elliptic curve over F. Say of conductor 1, if we're working with the full SL2OF. And then we obtained a class in D-1 cocycle on SL2OF on the Hilbert modular group with values in analytic functions, but not quite on the full space of analytic functions, modulo a certain group of periods, a finite degenerate Z modulo of rank 2 in C. And an earlier conjecture of Oda predicted that the periods of this cocycle we had constructed were actually commensurable with the Néron lattice of the elliptic curve E relative to a suitable real embedding of F into R. And so then it was very natural to conjecture, and I made this conjecture with Adam Logan, and we tested it numerically in a number of examples, that if T is a torus, as in the previous slide, now we can look at the value of this elliptic cocycle at T, and we obtain now an element in here, in the HD-1, with values in C modulo lambda E, which is this again, which is C mod lambda E, which is identified with E of C. So you get in this way a complex point on the elliptic curve over F, and so this would seem to be playing the role of a kind of modular parametrization. And indeed, we conjectured that the resulting complex point was actually algebraic and defined over some narrow relative Hilbert class field for K over F. Well, that was okay. So this process, so the idea of replacing the Eisenstein cocycle by an elliptic one suggested that somehow this whole philosophy of looking at modular cocycles and trying to approach explicit class field theory this way really does go beyond the framework of Stark conjecture, because we're not just producing units now, we're producing a sort of a larger class of algebraic objects. And in that sense, it's perhaps more reminiscent of the original framework of CM theory that was put forward by, or that was studied, that was proposed by Hilbert and so on. And so one question you could ask, I mean, there are several questions that arise from these works. One of them is whether Kopp's-Pochhammer cocycle for GL2 or the Eisenstein cocycles on GLN that Bergeron, Charleroi, and Garcia introduced, so their formalism suggests a natural extension to GLN, not just GL3, whether these constructions would admit similar cuspidal, therefore elliptic variance. And that's not so clear because that's something that would be very interesting to understand further. And another question is whether there might be meromorphic variance of these cocycles. So the point is that in CM theory, you're allowed to take any meromorphic modular function on your Shimura variety and evaluate it as CM point. And as long as the CM point is not in the locus of poles or zeros of the thing, you get an interesting class invariant. But with a non-trivial factorization, so certainly not a Stark unit. And whether this formalism does afford this in this case, so we would like to know whether there are meromorphic cocycles whose values maybe we give class invariants which are not directly related to Stark units, and therefore would have the chance of overcoming this kind of signature barrier, which means that the theory so far with Stark conjecture only allows you to study ATR or totally real fields. So that's the second question. So meromorphic cocycles, unfortunately, we have no examples basically in the purely Archimedean setting, which I've focused on until now in the talk. And so, but let me just say that, so, and this is a bit of a recap of what I've said until now, there's this kind of a dictionary between modular functions, which are the classical objects which we use to approach complex multiplication for CM fields, and these modular cocycles. So, in the classical setting of modular functions, you have modular units or their logarithmic derivatives, which are Eisenstein series of weight 2. And the analogous object in the world of modular cocycles are these Eisenstein cocycles. I think Jean's cocycle is part of that world in some sense, although it's kind of, it also has some tantalizing differences. And there's certainly the Bergeron, Charleroi, Garcia cocycle, or this Eisenstein cocycle in the Hilbert modular setting with Pierre that I evoked later, are examples of that. So they really play the role of Eisenstein series in the setting of this theory. And in all cases, we have a kind of Kronecker limit formula, which relates the resulting values to leading terms of L functions, therefore confirming, I mean, showing that our predictions about explicit class theory are consistent, at least, with Stark conjecture. Now, we also have modular parametrizations. And this elliptic cocycle J sub E is exactly what plays the role of the modular parametrization in the setting of Hilbert modular varieties for totally real fields of larger degree than 1. And in both cases, well, in the classical case, there's the Gros-Zagier formula, which relates the resulting Heegner points and their heights and so on to central critical values, in fact, of L series. And we believe that there's a similar Gros-Zagier formula, but we can't prove it because we can't even begin to talk about the heights of these points because they're only conjecturally global, but there ought to be a Gros-Zagier formula as well. So these things should be related to L functions. Now, what about meromorphic modular functions? Well, those would be, the analog would be meromorphic cocycles. So you would relax the condition that the cocycles take values in analytic functions in some sense. And here, we don't think that there would be at least any simple, straightforward, natural connection with L functions. And one reason for wanting to find this kind of situation is that then one would feel that one has really gone decisively beyond the framework that Stark was proposing. I should say that these elliptic cocycle values, which play the role of Heegner points, we call them Stark Heegner points because there's this feeling that they really do fit in the framework. I mean, they ought to have this connection to Hasebe L functions of elliptic curves, therefore. But the objects in the third row of my table would really be something that I think goes genuinely beyond. But unfortunately, the construction of these meromorphic co-cycles in the purely Archimedean framework remains speculative. So the main reason, and so one can ask in particular whether one could perform such an extension for the very tantalizing sort of theta co-cycles that Jean Cobb has constructed for real quadratic fields. Now, so far, the best evidence I can offer, and the reason why this is not just a kind of empty speculation, is that there is a good evidence for the existence of these meromorphic co-cycles and their desirable values, properties in the non-Archimedean setting. So you can formulate a lot of non-Archimedean analogs of these purely complex constructions. And one has there somehow, in some sense, a much more satisfying, complete picture in the current state of our understanding. So the most simple setting is the setting of what I call Ihara co-cycles. So for the Ihara co-cycle, you look at, the simplest setting is that you take a group like SL2Z1 over P, which is sometimes called the Ihara group because Ihara was the first to really seriously study its group theoretic properties. You show that it's an amalgamated product of two copies of SL2Z, for example. And the natural non-Archimedean symmetric space in which this group acts is the p-adic upper half plane, so-called Drinfeld upper half plane, which is the complement of P1QP and P1CP. And a rigid analytic / meromorphic co-cycle, eventually modulo periods, is going to be something in one of these groups. So they're going to come in several different flavors, these Ihara co-cycles. They could be taking values at A star, which is the multiplicative group of rigid analytic functions on the p-adic upper half plane. They could take values in M star, which is the multiplicative group of rigid meromorphic functions. So functions where we allow poles and zeros at some discrete collection of points on the p-adic upper half plane. Or finally, the third variant is you could take A star modulo some rank 1 lattice, the multiplicative group generated by some element Q with non-zero valuation in CP star. So these are the three variants. Now, if we have such objects, we can evaluate them at special points, which in this case are defined over real quadratic fields. So you take a tau in HP, intersect at some k, where k is real quadratic. In that case, the stabilizer of tau is rank 1. It's generated by a matrix, which essentially corresponds to a fundamental unit in the associated real quadratic field. And then we define the value exactly as we did before by restricting the cocycle to gamma tau and evaluating at tau. And that gives us a canonical multiplicative invariant. This invariant is going to live in CP star if we had an analytic cocycle. It'll live in CP union infinity if we have a meromorphic cocycle, because you could have zeros or poles. And it'll a priori, and it'll live in CP star mod Q to the Z in the third setting if we have an analytic cocycle defined modulo periods. And this quantity is just called an Rn value. It's generally conjectured that it will be, in some sense, algebraic and defined over a suitable ring class field of the real quadratic field, which is associated to tau. There's a sort of a natural order in the real quadratic field associated to tau, and that's what should happen. And this is what happens. So this now emerged a coherent, but still largely conjectural picture of what happens with these Rn values. But one can say that these Rn values definitely resonate with analogous phenomena in the setting of CM, or imaginary quadratic fields, in the classical CM theory. Namely, we have an Eisenstein cocycle defined on the, so one cocycle on the Ihara group with values in A star mod P to the D. So it's one of these cocycles modulo periods, but the period is very simple, it's just the prime number P. And the Rn values give us units, well, not units, but actually P units. Elements which are units everywhere except at P. They're so-called gross Stark units, and they arose in an analog of Stark's conjecture for p-adic L functions that was formulated by Gross. And so we conjecture that these values belong to these P units. And in fact, this we can in fact prove now. It's largely something that's within the reach of existing techniques because the p-adic variants of Stark's conjecture are much more accessible. That's something that we've certainly understood in the last decades than the original Stark conjecture. It's easier to construct P units than it is to construct units in some sense. Now, for the elliptic curve of conductor P over the rationals, one can also construct a rigid cocycle analytic, but modulo periods. But now the period is more interesting. It's actually the Tate period that arises in the p-adic uniformization of this elliptic curve, which has multiplicative reduction at p. And then we can take the values of the cocycle. They live in Cp star mod q to the z, which is identified with E of Cp, and we conjecture that this resulting point is actually defined over the Hilbert submarine class field. Okay, and then finally, for any Rm point, if we have a rigid meromorphic cocycle, we can look at its values at the Rm point. And in fact, we can construct a lot of them. There's the group of rigid meromorphic cocycles of infinite rank over Z. And so there's this rigid cocycle for which for every tau, which is at Rm point, you can find one whose zeros and poles are in some sense concentrated on the gamma orbit of tau. And then we can take some cocycle like that, call it J tau 1, which has zeros and poles only at tau 1. And you should think of that as being an analog of J of Z minus J of tau 1. So because that would be a modular function which has a zero only at tau 1 and or on the gamma orbit of tau 1 and the pole at infinity. So this J tau 1 is like the analog of J of Z minus J tau 1, and you evaluate it at tau 2. And what you get then is an object in the theory of real multiplication, which behaves like little j of tau 1 minus j of tau 2, the difference of j invariance for classical singular moduli. So we think of this quantity as a difference of real quadratic singular moduli. Okay, and these are the kind of objects which we would very much like to have complex analytic variance of. I'm going to say now a few words about what we can prove in this third setting about the algebraicity of the corresponding invariance. So I'm going to now look at this J tau 1 of tau 2. So this is a quantity which is conjecturally defined over this abelian extension, or this compositum of abelian extensions of Q of tau 1 and Q of tau 2. But on the other hand, it also belongs to a quadratic unramified extension of QP. So I'm going to take a slightly weaker invariant where I take the norm from QP squared down to QP. This is a bit an analog in what you do in the Archimedean setting, where you take the absolute value of a complex invariant. So what I'm going to describe now is a little bit weaker than the original conjecture because we're only considering this absolute value in the p-adic setting. Okay, so if tau j is in Q square root dj for j equals 1, 2, I'm going to assume that I have two discriminants, d1 and d2, which are relatively prime to each other for simplicity, and both fundamental, say, both discriminants of real quadratic fields. And I'm going to assume that these two discriminants are not divisible by p. And for tau 1 and tau 2 to be in the upper half plane, it has to be that this prime p is inert in both Q square root d1 and Q square root d2. It has to be inert in both quadratic fields. And I consider this involution, which sends root dj to its negative, so the natural algebraic involution on the quadratic fields. And to such a to these tau 1 and tau 2, I can associate natural geodesics on the classical Poincaré upper half plane. That is, if I have tau 1, I can look at its algebraic conjugate, think of them as real numbers. So they live on the boundary of the Poincaré upper half plane, and I can draw the geodesic, the semicircle, joining those 2 points. And I get a nice hyperbolic geodesic on the upper half plane. And I'm going to call the one associated with tau j, I'm going to call it gamma j. So I have 2 geodesics, gamma 1 and gamma 2. And I can then look at their topological intersection on the upper half plane. So if you have 2 geodesics, either they intersect or they don't. If they don't, the intersection number is 0. If they do, it's going to be 1 or minus 1, depending on a choice of orientation that you make on the upper half plane. You make a consistent choice, of course, for all cases. And now you can associate to a pair of real quadratic numbers a quantity which we think of as a local Green's function. And it's going to, the interesting feature of this formula, it's a very simple formula, but the interesting feature is that it mixes together both p-adic and Archimedean information. So what we do is we take in the numerator the difference tau 1 minus tau 2, and then we take the norm. So we multiply by the conjugate tau 1 prime minus tau 2 prime. We divide by this quantity in the denominator, which is not very important. It's essentially some multiples of the discriminants of the 2 fields. And we think of this quantity as a p-adic number. It actually belongs to the middle quadratic field, the quadratic field Q square root of d1, d2. And we can embed this in the p-adics by choosing the. So that, and you'll also observe that it's a cross ratio of involving these four numbers, tau1, tau2, and their conjugates. But we raise it to the power of the gamma1 dot gamma2, this topological intersection of the corresponding geodesics on H. And this number is either 0, 1, or -1. So if it's 0, it means that this quantity is just going to be equal to 1. So in an infinite product involving them, we're going to be suppressing those terms. Okay, so this belongs into this field a priori, but we're going to think of it really as a p-adic number. And from its definition, you see it involves a cross ratio of this topological intersection. You can see that this function is what you could call a point pair invariant. If I take tau1 and tau2 and I simultaneously translate them by any matrix in SL2Q, then I do not change the value. The cross ratio is invariant, and likewise, the topological intersection of the geodesics is not going to change. Okay. Now, we're going to combine these local Green's functions to a global one by taking some product over translate. So the idea is that we want to make this a function which is invariant under the action of SL2Z on both arguments separately. And so to do that, we of course, this gamma acts on real quadratic elements by Mobius transformations, and it also acts on the matrices by both left and right multiplication. So if I let gamma1 and gamma2 be the stabilizers of my real elements, tau1 and tau2, so these are both groups of rank 1, as we said before, then I can take the following infinite product, which I'm going to call capital GM of tau1, tau2. I take the product over the matrices of determinant M, but modulo gamma1 on the left and modulo gamma2 on the right. And I just take this local Green's function, evaluate tau1, alpha, tau2. Now, it's not hard to see that if I multiply alpha on the right by something in the stabilizer of tau2, I don't change this expression. If I multiply on the left by something in the stabilizer of tau1, I can bring that guy on by the point pair invariance property, I can bring it to the tau1, and then it's, so this thing is really well defined. It's defined on this double coset space, firstly. And maybe what's less immediate, but you can check, it's not too hard, is that this product is really a finite product. Because of this decision, this definition where you suppress the terms if the corresponding geodesics do not intersect, you get only as many terms as you would have when you compute the intersection of the two geodesics in the quotient of H mod SL2Z. And that's going to be involving a finite number of quantities. So it's really a finite product in this quadratic field. So that's what I'm saying here. And okay, so now I should remind you that I'm assuming implicitly that P is inert in both these quadratic fields, Q square root D1 and Q square root D2. Therefore, it's split in the middle one, Q square root D1, D2. And therefore, these elements, I'm thinking of them really as elements of QP. They're just p-adic numbers. And I would like to take suitable limits. And so I'm going to assume to begin with, first, and in fact, that's all I'm going to say. I'm going to assume for simplicity that the prime P is one of these 5 primes, which have the special feature that the corresponding modular curve associated with the Hecke congruence group, gamma naught of P, has genus 0. So there's no cusp forms of weight 2 in these levels. And then the theorem that Vonk and I prove is that the limit, if you take this GD, but you look at G sub P to the N, but you let N go to infinity, so you look at larger and larger powers of P, so these finite products remain finite at each step, but there's about more and more terms. So in the limit, you get something which could converge to something interesting, something outside that quadratic field. And it exists, so it exists as a p-adic number. That's the first part of the theorem. The second is that it does belong to the compositum of these two Hilbert class fields attached to tau1 and tau2. And furthermore, we can study the factorizations of these quantities, and we see that the factorizations have very much the same patterns as what appears in the difference of singular moduli. So Gross and Zagier have a very influential and beautiful paper from the mid-1980s where they study the factorizations of J of tau1 minus J of tau2. They find that these quantities are divisible by all kinds of small primes, but they can give a precise recipe for what are the primes that divide it and so on, and the norm. And all the phenomena that they observe in this case have their counterparts in the factorizations of these real quadratic singular moduli. So it really is justified to think of them in this way. Okay. Okay, so now I want to conclude my talk by saying a few words about a possible generalization of that formula to the setting of GLN. And that was something that was suggested to us by this work of Bergeron, Charolois, Garcia. We very much wanted to extend the formalism beyond the setting of GL2 in natural directions to try to see whether there are GLN co-cycles and whether there's a similar theory there. And what I'm going to present, we are not yet able to define genuine GLN co-cycles. That's still something that we don't understand. But at least the very concrete explicit formula I gave you for the norm to QP has an obvious counterpart in that setting. So I'm going to indulge in the last 10 minutes or so in a bit of speculation by writing down this formula and making a conjecture about its algebraicity. But anyway, it's not a very serious conjecture because it's not backed up by any either experimental or theoretical evidence at the moment. Okay, so here's the setting. So I take T1 and T2 to be maximal tori and GLN now. And I assume that they're totally non-split over Q. So they correspond to the multiplicative groups of two fields, K1 and K2, which are genuine, totally real fields now of degree n, in which the prime P is completely inert. So one of the things you can do, one of the features of the p-adics that the complex numbers do not have, is that if you take a field of degree n and you tensor it with QP, it can certainly happen that you still have a field. If you tensor it with R and the field is of degree more than 3, you'll never get a field, right? You'll get a bunch of copies of R and C. And so the fact that the algebraic closure of QP is of infinite degree over QP is somehow a key difference in this thing that allows us to have this kind of phenomenon. Okay, so that's one thing where I think we have to understand better how to extend some of these ideas to the Archimedean setting. Okay, so if I have two such tori, well, I can diagonalize them. So I have vectors v1 and v2 and k1 to the n and k2 to the n, which are eigenvectors for t1 of q and t2 of q respectively for these two torus actions. So I fix two such eigenvectors. Of course, for each torus, there are n to choose from, and I just choose one in some way. And the ultimate goal then is to define a p-adic quantity, which generalizes the one in the previous slides, which I had for n equals 2. Okay. Okay, so as before, so there was an important role played in the background, in the side wings by this Poincare array upper half plane. For GLN, the analogous object is the group of SL and R modulo a maximal compact subgroup, which is the orthogonal group of dimension n. And the quotient SL and R mod SO and R can be identified concretely with this set of positive definite quadratic forms on R to the n. So if you take, so of course, SL and R acts naturally on the set of positive definite quadratic forms by translations of the variables. And the stabilizer of a point, so the standard dot product quadratic form, is going to be the orthogonal group. And so that identifies these spaces. Now, if I choose a collection, remember that K1 and K2 are totally real. So each of them has n real embeddings. And once I do that, I get vectors v1, 1 up to v1, n, which are obtained by taking this v1, which is in K1 to the n, and applying to it the n different real embeddings. So I get a collection of vectors in R to the n, and likewise for v2. Okay, so I get these n tuples of vectors in R to the n from both of these eigenlines or eigenvectors. Now, we can associate to the tori two different types of topological cycles on this Archimedean symmetric space, namely a small cycle, which I'll call little delta of T1. This is just a set of quadratic forms, the set of positive definite quadratic forms, for which V1I and V1J are pairwise orthogonal for all I not equal to J. So I asked for all the quadratic forms for which this V1 up to V1n, these vectors here, form an orthogonal basis. Okay? So that's delta to it. So I'm imposing a lot of conditions. I should have maybe said that the symmetric space X infinity has dimension n times n plus 1 over 2 minus 1. So it's roughly quadratic in it. That's what this cycle, delta of T1, here I impose a quadratic number of conditions as well in my cycle, and it ends up being of real dimension n minus 1 in X infinity. Now, there's also a big cycle, which I'll call delta T to T2, where you look at the quadratic forms for which the first vector, V21, is orthogonal to all the other ones relative to the quadratic form. Here I'm only imposing n-1 conditions, roughly, so I'm imposing a linear number of conditions. And it turns out that then the cycle is bigger. Its dimension is roughly quadratic in n, but it's of codimension n-1. So these little delta of T1 and capital delta of T2 are cycles of complementary dimensions in the ambient Archimedean symmetric space, and therefore it makes sense, that's the crucial point, to talk about their topological intersection on this x infinity, which is going to be, again, a number between -1, 0, or 1. Okay, so now we turn to the p-adic picture. Now that we have these topological intersection numbers, we can define a local Green's function by now, starting with this V1, we embed it in Cp to the n by choosing a fixed p-adic embedding. And then all the other p-adic embeddings are related by Frobenius. So you can just obtain vectors V12 up to V1n by iteratively applying Frobenius to the original vector. And you get a collection, an ordered collection of n vectors. And likewise for V2. So these are these Frobenius translates. And now, to define the local Green's functions, I take some determinants. I take the determinant of V1, V22, V2n. So in the first column of my matrix, I put the vector V1. And in the next remaining n-1 columns, I put the Frobenius translates of V2. Okay, so there's V1 and V2 entering. And here I do the opposite. I put in my first column V2, and in the remaining columns, the Frobenius translates of V1. That's what happens in the numerator. The denominator is less interesting. It's just the determinants of the individual matrices arising from the V1s and the V2s. And I raise it to the power this Archimedean intersection here. Okay, so this is a p-adic quantity again, which plays the role that cross ratio we had before. And this exponent is a quantity that comes from real intersection theory. And again, this belongs to K1, K2. And maybe a more concise way of packaging this invariant is to say, well, when you have a collection of n vectors, you can also look at the dual basis. So I'm going to call V1 star, et cetera, the first vector in the dual basis associated to this collection of vectors, and V2 star is going to be the first vector in the dual basis. So you do that. So it's just V2 star of V1 times V1 star of V2, okay, to the power this intersection. So that's a more concise way of writing down what this G of V1, V2 is. Okay. And again, because of how determinants work, basically, it's easy to check that this is invariant under simultaneous translation of V1 and V2 by any matrix now in SLN of Q. Okay. And now we do what we did before. We try to package this into some kind of global object by making it invariant under SLNZ. So again, this acts on the tori, it acts on Mn of Z. So I take gamma 1 and gamma 2 to be the stabilizers of these vectors. And these stabilizers now are groups of rank n-1. They're isomorphic to the group of units in a totally real field of degree n over Q. And I take the same product over a double coset space, where now I take Mn of Z. I take the matrices of determinant M, n by n matrices with integer coefficients, and I take the product of these local things, G of V1 alpha V2. And again, this is a finite product, so it belongs to the compositum of the two degree n fields, K1 and K2. So it belongs to this field. But now I'm also going to consider GMN, which is just G of M times a power of T, T to the 2n. Okay, so that's just a little piece of notation. Now I want to make a conjecture about the existence of suitable p-adic limits involving these expressions and a prediction about the algebraicity of these limits. And so I choose a p-adic embedding of this field K1, K2, and now QP to the n. This is the degree n unramified extension of QP. And I take now I remind you that I have these local Green's function, the global object, which is defined in QP to the n, after embedding my fields K1 and K2 into QP to the n. And now, if I have any formal combination eta of integers, so here this AJ, MJ, these MJs are just positive integers, and these AJs are positive or negative integer. So it's just like something in the formal Z module generated by finite Z linear combinations of positive integers, okay? Now, whenever I have one of these gadgets, I can define a G eta n by taking the corresponding product of GMJs to the power AJ. Okay, so I just package this eta into a multiplicative product of the GMJs that I just defined earlier. And so the conjecture I'm going to make now about the existence, about the convergence of these infinite products and their algebraicity is going to be a little bit more vague than what I had for GL2. Namely, we just conjecture that there exists certain linear combinations of moduli, for which the limit of the G eta n's, so these corresponding multiplicative combinations, a value v1, v2, that this limit exists in 2p squared, but for any tori, t1 and t2. So this multiplicative combination is independent of the tori, right, that I choose to define it. And moreover, that it belongs to some compositum of the two Hilbert class fields of these degree n fields, the k1 and k2. It belongs to these the extensions up to k2, where hj is the narrow class field of kj. Right, so that's the conjecture, but I really hesitate to call it a conjecture. There's really no evidence for it now. It's very speculative, but it was very much inspired by the work on GL3 and GLN that kind of appears in this very recent paper of Bergeron, Charles Garcia, and so we're happy to acknowledge the influence of these ideas in this lecture. And I sort of conclude by saying that I hope that what happens in Baton Rouge stays in Baton Rouge. As far as this conjecture, I should have maybe called it more like a question or a speculation than a conjecture at this point. But anyway, I think it would be very, very nice also to have serious experimental work trying to evaluate these infinite products to high accuracy in a reasonably efficient way that then these predictions can be tested numerically. Okay, so in conclusion, I just want to say that the traditional approach to explicit class field theory via CM theory is based on CM values of modular functions. That was the sort of the beginning, what I sort of mentioned in the beginning of my talk. So, and you can think of a modular function as a class in H0 of gamma A of x, where gamma is some arithmetic group and A of x is a space of analytic, for example, or L2, whatever, some kind of nice space of functions on a symmetric space, where x could be some G of R modulo compact, for example. So that's the traditional framework. That's the framework of Shimura Taniyama. We're beginning to see sort of the bare outlines of a maybe general approach where you have to replace modular functions by some kind of co-cycle on an arithmetic group. So maybe one element of answer to Hilbert's question, what plays the role of modular functions in constructing class fields in greater generality, is that you have to replace modular functions, which are classes in H0, by modular co-cycles, which are classes in a higher degree of cohomology. And all the mystery, of course, in the theory arises when the degree is higher than 0. But anyway, so it's clear that these objects are kind of an independent interest, and they're certainly implicit in a lot of the literature, starting at least with the work of Eicher, Shimura, and maybe even before that. I mean, the idea of looking at cohomology of arithmetic groups is, of course, fundamental to the subject. So, but in the context of what I've explained, especially towards the end, I mean, the thing has become gradually more and more speculative, and there is really a lot that remains to be understood. So I'll stop here, and thank you for your attention.
Well, thank you very much for the excellent talk. Maybe we see whether any online question first. Any question from the audience? Okay, Jean.
Yeah, have you thought about any either for the BCG co-cycle or any of the other cubic or higher degree co-cycles evaluating at partially split tori?
So that's a good question. Generally, I mean, you want the numerology to work out, of course. So you would like, as I think, that the group of integer points of your torus should at least be equal to the degree of cohomology.
Yes.
And no, I don't think we've really looked at any cases like that. It might be interesting to do
like
that.
Imaginary quadratic for SL3.
Yeah, for example, yes. So if you take, so you're thinking of like the BCG co-cycle, and you would take some metal algebra, which would be But that wouldn't quite work, right?
Cross R that wouldn't work.
No, because then you would have units. It would be like K cross Q, right? Where K is
Yeah,
imaginary units.
K
Then the
cross
units would be like rank 0. But real quadratic.
Okay,
Yeah.
maybe that's what you want.
Real
Yeah,
quadratic
let's-
would be interesting
well,
indeed.
Just for okay,
It's-
for rank, is it exactly the units? Because it's like for
Yeah.
maybe we talk later, but
Yeah.
this is like was like the parabolic points for Q cross
Maybe,
Q,
yeah,
like
maybe there's,
that.
yeah,
So
you're right that, I mean, sometimes these co-cycles will kind of evaluate also at parabolic elements, which is a bit of a degenerate case. So you don't evaluate them at genuine tori, but at parabolic subgroups, and one gets interesting range that way as well.
Yeah, maybe I don't mean
So-
tori, maybe I mean
Maybe
parabolic.
that, yeah, and I'm not aware that that's been done for the BCG thing.
Do you have a quick question?
Have you tried to connect this to the Milson theory of special cycles?
Oh, absolutely.
Can you repeat the question because
Oh,
for the online?
So the question was whether this picture connects to Kudla-Milson theory, and the answer is absolutely yes. I mean, so there's one thing that I did not mention in this talk. So there's another possible generalization of the GL2 co-cycle. So you can move towards GLN, and I wanted to talk about that but you could also think of GL2 as being, or SL2 as being an orthogonal group of a quadratic space of signature 2, 1. And in the Kudla's theory, one has a very rich theory of Shimura varieties on orthogonal Shimura varieties of signature 2n and special cycles on them and so on. And so with Leonard German and Mike Lipnowski, we wrote a paper on rigid meromorphic co-cycles for orthogonal groups. And there's a general picture there, which is quite complete, again, lacking a little bit in experimental testing. But if you have an orthogonal group of a quadratic space of signature RS, you can associate to it a collection of rigid meromorphic co-cycles, which are in the HS, the S cohomology, of gamma of a p-arithmetic group in the orthogonal group, with values in the multiple group of spatial functions on a suitable p-adic analytic space. And yeah, so then we can make, we sort of expect that the values of these co-cycles at special points on the p-adic symmetric space have algebraic meaning.
There you have
But
an
that's-
explicit integral transform called the theta correspondence.
Absolutely, yes. So
Things are expressed in periods of theta elliptic.
yes, absolutely. And there, so that I would say the answer is half-half. So we have a Borcherdt's theory. So Borcherdt's lift, for example, tells you if you want to construct meromorphic automorphic forms on the orthogonal groups, you can obtain them as the theta lifts of weakly holomorphic modular forms on GL2. What we can show is that the principal parts of weakly holomorphic functions, classical weakly, encode the divisors of our rigid meromorphic co-cycles. And therefore, and the way that that's proved in Borcherdt's theory is via the theta lift. And our result is a little bit more indirect. I mean, we prove an analog of the Gross-Conen-Zagier theorem, which is that these special values or certain obstructions related to special values can be encoded, can be packaged in the Fourier coefficients of certain classical modular forms. And yeah, so it's sort of there's a similar story, but there are certain interesting ingredients that you see in classical Borcherdt's theory and Kudla-Milson and so that are lacking in this picture still. So I think there's still interesting things to be done there.
Okay, Joe, is there another question online? Okay, if no, let's send Henri again for the wonderful talk. So let me make